the last gas law problem, which technically is not really a gas law. It's actually using something from physics called the concept of work and applying it to a gas, but still gases, so we'll call it a gas law. We don't work, I just said the word. We need to know what work is. That's the equation and the definition of work. Work is force being applied to an object, a force, a push or a pull to an object, and you get it to move. If you can push or pull an object and move it, you're doing work. But we don't want that definition. What? No, we want the gas application definition of work. Yes, you do. Okay. Work is equal to pressure. Pressure is force per unit of area, so it's analogous to force because it's force, but just over an area. So it's force, kind of. And distance, we're not talking about moving something a certain, did I move it 2 meters to the right, 2 meters to the left? No, we're talking about a gas expanding or contracting. It's moving. A gas expands or contracts, it moves. And that is a change in volume. And the change in volume is analogous to our distance that we move something. So this is the equation that we need to use for gases when it comes to work. All right. So let's dive in here and see what's happening in this problem. Oh, one more very important thing. There are two different works. What do you mean two different works? Well, notice that. Okay. You can have positive work or negative work. Positive work or negative work. What? I don't get it. I don't get it, man. Explain it. Okay. Let's say that I'm doing some exercise. Need to get more exercise. I mean, I've been sitting around too much and eating and getting fat. Not PHAT fat. I'm going FAT fat. So let's get some exercise. Let's lift some weights. Let's lift this. Whew, that was exhausting. Try it one more time. I did work. I'm exhausted. I did work on the marker. Work was done, okay, by me on the marker. By me on the marker. By me on a marker. One thing's loss of energy is always another thing's gain of energy. Energy, you're not talking about energy, you're talking about work. Work is how energy is transferred, so technically work is energy. So we're talking about, work was done by me, I lost energy, hence the negative. Work was done on the marker, gained energy, hence the positive. Okay, we need to know that. That becomes important in a minute or two. Here you'll see. All right, I think we're ready for the problem. Okay. What do we got? A gas expands in volume from 13 milliliters to 15 milliliters at a constant pressure. Okay, calculate the work done if the gas expands against, I'm going right to B, forget A. If we were in class, I'd explain it. I thought it was interesting, but I just want to take these, you just got to move, man. Just got to move, okay? Forget A. You're not going to know. B, you got to know how to do. B. Work done if the gas expands against a pressure of 2 atmospheres. So this gas is going to go and expand against a pressure out here of 2 atmospheres. And it's going to take some work to do that. The more pressure on the outside, the harder it is for the gas to expand, and the more work it has to do. So the pressure is important. The pressure is in atmospheres. So we just are so tempted to take that 2 atmospheres and put it right there and piece of cake. We can't. Hate chemistry. Well, why not? Because this equation is based upon physics units. Make it long story short, we're not using atmospheres in physics. It's used kilopascals. So we have to go with kilopascals with a physics-derived equation, kPa. But we remember what the kPa value is for standard pressure. It's 101.3 kPa. So 101.3 kPa is equal to 1 atmosphere. Okay, it's one of those standard pressures you should know. Well, this says 2 atmospheres. So what's my kPa value? Double it. Just double it. 202.6 kPa would be the pressure I would use in this problem. Not atmospheres, kPa, 2 atmospheres, double your kPa, 202.6. Volume change. Oh, that's easy. I mean, just check the difference between the two numbers. You got 13 and now you're at 50. That's a difference of 37. So we'll put 37 in there, right? No. Chemistry. Because this unit has to be in liters. Okay, has to be in liters. So if it's in liters, 37 milliliters is 0.037 liters. 0.037. I think we're ready now. I think we got it. Got to be in kPa. Got to be in liters. Tricky. So if I do the math, let's do the math. You should do the math too. You should be doing this at home. So you shouldn't trust me. A guy wears this kind of shirt, don't trust him. 7.49. Let's see what the answer is. Please. 7.50. I'll take it. Oh, I'll take it. Now, if you notice on the answer sheet, I also wrote by. So I wrote 7.50 by. Why'd you do that? Because this is the amount of work that was done by the gas as the gas is expanding. The gas has got to do work against the atmosphere. Works done by the gas on the atmosphere. All right? That problem. Solve it. Keep going. One more. Okay. The second problem in this little subset of problems, the work done to compress a gas is 95 joules. In the process, 31 joules of heat is given off. Calculate the energy change of the gas. This is going to use another equation, not the same one I just used. Actually, a different equation. Now we're getting into thermodynamics. We're segueing. This problem here is a segue going from gases to thermodynamics. So the next several problems are going to deal with thermodynamics. Now, heat. Thermo means heat. And in dynamics means to move. So thermodynamics, moving heat. Now, this equation has to do with what's called the first law of thermodynamics. And you know the first law of thermodynamics. You just don't know you know, but you do. So I'm going to take the chemistry that's deep down inside you and bring it out and make it blossom. You know that energy cannot be created or destroyed. Just change in form. That's the first law of thermodynamics. Now, that's the wordy part. There's an equation that goes along with it that looks like this. That's a delta U. Okay, equals Q plus W. This we already know is work. We just went over that, people. That's work. This is Q. That's heat. And we better know that for the rest of these problems that we have to do for this set. Q is heat. What's this bad, Larry? That is change in internal energy. Internal energy. A little neater. Internal energy. Internal energy is the sum of all the kinetic and potential energies of a system. What's a system? Anything you want it to be. It could be this marker, my system. You could be a system, whatever we define our system to be. But whatever we define our system to be is the sum of all the kinetic potential energies that thing has. So you have some internal energy. Now, what is this equation saying? We can change our internal energy. We can do it in two ways. There are only two ways to change the internal energy of anything. Anything. Well, how could we do it? So we could change the internal energy by either, or we can do both. Cranking up the heat on it. You want to change my energy? Throw me into a fire. Oh, and I'm pretty sure some of you probably want to do that right about now. Okay, yeah, I know you do. I know I can read your mind. Put some heat on me. That'll change my energy. Hot. The other way is to do work. Do work on something. Like earlier, I said we're going to move the marker. So move the marker. Work done on the marker gives it more energy. Now it has a higher internal energy because I gave it some energy. We can also heat it. We can put a Bunsen burner, torch it with a Bunsen burner. That will also increase the kinetic energy of the object. So we can do it in two ways. Let's do a chemistry example here. Let's see. Actually, I can do that one, but let me do one quick example for you. That's not the problem, but I think might clarify this. Beaker. Water. Water in the beaker. You've got it on a hot plate. See, it's a very hotty looking hot plate. Crank it up. Put some heat into it. There are two ways you can increase the temperature of that water. One, we'll turn on the hot plate. That'll do it. That'll pump heat into it. The other way is you could take like a spoon and move it around. You could take a spoon and twirl it around. That's a spoon. Thank you. I know it's a good drawing. Twirl it around. You, by putting energy into it, by twirling it around, you're going to heat it up. You try this at home, not for professionals only. Take a bottle of water, your Dasani water, whatever you drink. And who would have thought, 30 years ago, back when I was, in my 80s, I never thought that people would drink bottled water. It's crazy. Anyways, bottle of water, half gone. Take it, shake it. Shake, shake, shake. Shake, shake, shake. Shake your booty. Shake your booty. I've got great lyrics. I've got to write some songs. Do that for about 5 minutes. Take the temperature of it. And actually take the temperature of it before you start shaking it and see the comparison between the two. It will go up in temperature. You're adding energy to it by moving it. So moving it and heating it will change the internal energy, the energy of the system. Okay, let's try this problem. This problem says, the work done to compress a gas is 95 joules. Work done to compress a gas is 95 joules. In joule, just bear with me. I'll come back to what a joule is very soon. We have to do a heat problem next, so we'll have to know about the joule. 95 joules. In the process, 31 joules of heat is given off. In the process, 31 joules of heat is given off. What's the change in internal energy? Now think about this. We're not going to do the math yet. Stop. Don't look. Stop it. Stop looking. You're doing work on the gas. And that's why, by the way, I'm going to use positive here. And it says, the work done to compress a gas. Now, if you're compressing a gas, here's you. And you're going to take this gas and compress it. Work is being done by you on the gas. So on the gas means that work will be a positive value. So we'll be adding a positive value. Now at the same time, we're losing heat. Maybe you're doing this, you took the gas, your balloon, you took a balloon, helium balloon, and you took it outside on a January day and you're compressing it. So not only are you compressing it, but it's losing heat because it's cold out. So it's losing 31 joules. Losing 31 joules. We have to put a negative there. We're losing the heat. Losing. Do the math? You got it. You do that, you subtract the, we take the negative 31 and add 95. Same thing as subtracting this from that, you get 64 joules. So the change in internal energy is 64 joules. We've gone up in energy. True, we lost some energy because there was a temperature difference and the balloon that I'm squeezing is losing energy to the environment. But at the same time, by squeezing it, I'm doing work on the system and that increases the energy to the system.